Okay, good morning, everyone. Mike, thank you for having a session for talking about energy. I also wanted to thank Todd for everything he did for the program. Mike and Todd have been just incredible. Later on, I'll tell you a little bit about the history of our program and share some tidbits. So today, I was asked to speak about sustainable energy, and energy is a vast issue. And we're going to have several sessions later in the day on different aspects of energy. So I decided to focus my presentation on what I am a real expert in, which is electricity. So I want to talk a little bit about this story on how do you decarbonize and make the electric grid more resilient, but instead of from the top down, doing it from the bottom up. So using what's called distributed energy resources. So the electric grid is 120 years old. And for most of this time, it has kind of worked in the same way. And it's shown here in this picture. We have large generation stations that are placed behind transmission lines, typically away from the consumption centers. And they generate power that flows through the transmission lines, flows through these substations. Those are the wires you see next to your home, and then comes to homes and businesses. The system is organized so that generation and utilities meet at a wholesale market that's run every hour, and they trade energy. And what utilities do is basically they are our representatives. They aggregate all of the demand under their jurisdiction and make sure that enough electricity is purchased to service everyone. In the traditional grid, the visibility utilities had about us was limited to the meter. And generation was super predictable, as well as typically very carbon intensive. What is happening? We have a changing grid. First of all, on the transmission side, we are seeing a very fast-paced adoption of solar and wind, as well as storage. So in the past grid, there was no real way to store energy at a large scale. So what that meant is at every minute of the day, every second of the day, you have to have the ability to produce the amount of electricity you're going to consume. If the timing of that consumption doesn't match, then you're in trouble. But storage can help you because it allows you to shift consumption over time. Another major change that's happening to the grid is really on the consumer side. Today, we're seeing a massive adoption of what are called behind-the-meter devices or distributed energy resources. Those are things like rooftop solar panels, smart appliances, electric vehicle charging, and all of these devices are connected into clouds, and data is collected from that, and some sort of minimalistic management is done with these resources. So in this new grid, there is this kind of question of how do we ensure that supply and demand can be balanced at a very low cost when we have this much greater presence of renewables. We don't want to just use a massive amount of storage. That's kind of expensive. So one of the approaches is to really leverage these distributed energy resources. So just to kind of show a little bit more of these distributed energy resources, they can be rooftop solar. There is even wind turbines, individual wind turbines, Tesla Powerwall and different types of energy, electrochemical energy storage at home, EV chargers, industrial fans, the HVAC in your home, water heaters. All of those form the category of flexible loads. So typically we have three classes of DERs: renewables, storage, and flexible load. So how much of this is actually going to be out there? So we did a very careful kind of review of this, and I can share the slides of that review. But here I just kind of summarized it. And basically, we are looking out to 2050, and with the decarbonization goals identified by IPCC, we are going to have a dramatic increase of solar and wind, where they will start to account for 56% of the installed capacity in 2050. That's about a 10x increase, 8 to 10 times increase on what we have today. And distributed solar and storage, which are like two large components of DERs, will account for 13% of installed capacity in 2050. EV energy consumption is going to grow to 1,290 terawatt hours by 2040. So that's about 10 times increase as well. And we are expecting about 5,000 gigawatt hours of battery storage to be deployed in the grid. Now, when you have these changes, what are some of the challenges that happen? The first one is if I just added renewables, wind and solar, here's kind of in this first panel, the challenge is shown. In red is the electricity demand, what you consume. In blue and in yellow, I'm overlaying multiple days of wind power production and multiple days of solar production. And so the dark blue there in the middle is kind of the average of a wind day. And it's very clear that the sum of the yellow and the blue doesn't really match the red. And that's the challenge. So that's called poor demand correlation. We need to figure out how to make the sum of yellow and blue match red at the lowest cost possible. That cost is called the cost of integration. Another way of seeing this problem is kind of shown on the figure on the right-hand side. It's called the duck curve, and it's basically the net load, the load subtracted off of all the renewable production. And in California, we have a lot of solar production, and so what you will see is this big belly, which is essentially when solar is being produced. Now, why is this an issue? If you look at the topmost curve, that's how it used to be before solar. What it means is generators didn't have to accelerate and brake a lot while they were running. So they could last longer, it was cheaper, and of course, there were far less emissions. But now as we make this duck curve deeper and deeper, if you don't do anything about it, your generators have to decelerate when the duck curve is going down, which means I have a lot of solar production, and then, decelerate, and then accelerate when it's going up. So that's kind of what's called the ramping issue. And right now, the numbers here in California are staggering. We need something like 13,000 megawatt of power ramping in just 3 hours. And this is really tough to do. Okay, so the second type of challenge is more about electrification and what these new loads impose. So we had this question, if we end up with the EV penetrations that are being talked about out here in California and the West Coast, and generally in the United States, what is the impact on the grid? There's a lot of conversations going on saying, no, the grid can take it, and so on and so forth. Yes, it's true, up to if 10 to 20% of the vehicles are electric. When you go past that, there's a real serious problem to the grid. And here's one particular scenario we looked like, which is kind of the likely scenario based on modeling EV adoption over time up to 2040. And basically, the grid peak power would increase by 25%. That means you need a quarter more generation just to satisfy your EV load. To put this in perspective, maybe in the last 40, 50 years, we have seen demand decreasing because we have had energy efficiency, and a lot of our industrial production has been moving offshore. So we have been dealing with a grid that, has nowhere near 25% more capacity. The other issue that we will see is that as people start to charge these vehicles, particularly through fast charging, our local networks of power will be very taxed. When you connect anything in your home, if you've gone camping and you had a little generator and you connected something and you went a little beyond the capacity of the generator, it will either trip or you will see lights dimming and things oscillating. That's exactly what happens to our distribution network as we start to add a lot of EV charging happening simultaneously and at high speeds of charging. So we have a paper that's coming out in Nature Energy in the next couple of months that really goes deep into this issue and tries to figure out what's the best way to address it. So two big challenges, demand correlation and challenge of EV penetration. So what can we do? So one observation is that all of these distributed energy resources I talked about, they're typically uncoordinated. That means sometimes you have a little controller, maybe you own a Tesla solar panel and battery, so they put a little controller in your home that matches the two. And maybe your Nest thermostat is kind of connected to the cloud and adjusting the temperature based on whether you're home or not. So what we have is a system where all of these devices are connected to different private clouds, and they do some sort of minimalistic optimization. But that optimization doesn't really account for carbon, nor for what the grid and your local system can provide. So it taxes all of these systems, and as a consequence, if we want to support all this, costs will skyrocket. That's the reality. But what could we do? Well, what you can do is to start thinking about how to coordinate these things. And there's really two levels of coordination. One is called behind-the-meter coordination. That means on every kind of consumer, maybe Stanford is one very big consumer, I am another smaller consumer. I can have some local intelligence and decide how to optimize the functioning of my home and all the devices I have so that I both minimize cost for me and my pocket, as well as achieve other objectives like grid stability and issues with, for example, carbon, minimizing carbon. But interestingly, you can also do another sort of coordination, which is if we all can work together, then we can coordinate to match what the grid is providing us. So if we know there's a lot of solar at noon, and we could have enough flexibility on our EV charging, then we could ensure that all the EVs are charged at noontime by using technology and optimization. Okay, so that's the promise of DR coordination, and we have several studies now that show that this can actually address a lot of the issues that we raised there, including the local stability of the power network, reducing electricity costs to consumers, mitigating the duck curve, and providing general resiliency against grid failures. The easy way to understand about this is, if you have solar and storage for your own home, of course you can be safe from resiliency by consuming the electricity stored in your battery. But maybe you also have some excess amount of power there, and if you're locally connected to your neighbors, then you can share that power, provide value for everyone, and then increase the resiliency. So coordination can increase resiliency. So in 2016, we started looking at this, and we started this massive project called PowerNet. And the idea of PowerNet was, how do we create a technology that can make this happen using the cloud? The reason we wanted to use the cloud and not some custom server and hardware is because solving these problems needs scale. Things have to be easy to deploy, and they have to grow with the demand that we're going to have for it. So PowerNet is a project that resulted in a partnership of Stanford with Google, Sonnen. Sonnen is a battery a storage provider, and a company called Suntech Drive. They do basically industrial machine control. And we deployed PowerNet in various places, as well as one of the places was with our partner, the Navy. So what is PowerNet? PowerNet is an architecture that has several levels. At the very first layer, here in the leftmost side, we have a hub that's local intelligence that can communicate with resources that are enabled digitally, storage, EV charging, solar, as well as a smart panel. There is existing smart panels from various industry providers, But we also worked with a power electronics expert at Stanford to design a smart panel that had additional capabilities, including the ability to control power without just turning it off, which is the only capability that existed so far. Then in this hub, it's able to learn your preferences and optimize the combination of all these resources so that it minimizes your bill, as well as you can add other preferences, like maybe you want to take into account carbon and so on and so forth. This hub communicates to the cloud where it can participate in various forms of coordination. The simplest form is to say, we need to keep the whole grid safe, so please, whatever you do, make sure that, for example, we are not all discharging power from the batteries at the same time in a moment where the grid cannot take it. So that cloud coordinator is able to do that. And we designed the whole system, the software, the algorithms, and there's a lot of data science that goes behind this as well, so that it is very resilient to communication failures. It is aware of all of the power grid constraints. It is aware of user preferences and security, and it's fairly easy to scale. We had seen, when we started this project, we had evaluated about 100 different approaches to solve this problem. And all of them are fantastic in the lab. But what we found was when you put these 4 constraints, that's not what happens. So what did we do with PowerNet? PowerNet is a result of a team that had postdocs, several faculty, students, software engineers, and so on. The first deployment we did of PowerNet was to manage the cooling load in a farm. So given our time constraint here, this dairy farm is the largest dairy farm in California. It's called Double Diamond Dairy in Central Valley. It has 10 barns. Every barn has several of these industrial fans that are used to cool the cows. Now you might think, why are you worrying about farms? One farm like this, it's like me recruiting 700 homes for PowerNet. And we also went and recruited 20 homes for PowerNet, and it took me literally 10 times more effort to do than just this. So what do? We add solar, we control the fans, we added storage, and we have sensors that measure the animal health, the environment, and we added the intelligence to manage this. We also gave a simple user interface that the farm manager could use to see if the systems are working. Just this one simple user interface meant he could actually take off the 2 employees he had that have to go during the day across all barns and make sure these fans are working. What was the result of our technology? We were able to reduce the bill by 92%, and we are only reliant on 7% of energy from the grid, and we call that, a carbon, a resource, because in the grid you have carbon today. The next deployment we are doing is part of a program in the Sustainability Accelerator of the new school, and it's about how do we ensure 24/7 carbon-free electrification for campus fleets. So Stanford, in 2013, had a diesel bus system that emitted a lot of carbon per year, 2,800 tons. In 2020, all the buses are electric, and we have 38 buses, and these buses are charged from the grid. Now the question is this carbon-free? The first thing that one would think is, well, Stanford, at the same time, in 2022, just announced that we are a fully net zero campus. We produce as much energy, total energy, that is carbon-free as what we consume. So that comes from on-campus solar, as well as off-campus solar and some storage plant. Okay? Now, the question that I have for you is 100% renewable, or so-called net zero, enough to fully decarbonize bus charging? So let's see what happens. Here is kind of the pattern of bus charging. This is real data from the campus. Okay, you can see buses being charged at different times in the day. Here's the pattern of solar. So outside of that green area, you're basically charging from the grid. And it so happens is the times at which the California grid is at its dirtiest. So despite the fact that we are net zero, we are not carbon free. So here's kind of the emission signal from the grid in red. You can see it's the highest exactly outside of the hours of solar. That's because of the duck curve. So our question is, how do we solve this problem? How do we make the Stanford fleet 24/7 carbon free in a way that is cost effective, not by making anything more expensive? So we created this program with this mission, use PowerNet, our software platform, integrate some resources, and make this happen. And use this also as a living lab at Stanford to help others see the potential for carbon-free systems optimization. So just to quickly show here our approach, and our approach consists of 3 steps. The first is we predict the emissions that's going to happen in the grid. Next, we optimize the bus charging schedule in real time. And then we control and optimize storage so that it meets our carbon-free goal. So we are currently working in this project, and by the end of the year, we will have a demonstration for the Global Energy Forum. So thank you very much, and let me know if you have any questions.
Hi, I have a question for you. The figure of 5 on campus and 117 off campus, why isn't it the other way around? It seems you don't have resiliency, you have a total loss when you have the campus going off electricity for 1 week time. What is the plan to deal with this great problem?
Excellent. So one of the challenges of having a lot of solar on campus is you have to have appropriate locations for deploying solar. And the cost of solar that's on the rooftops and so on is higher still than the cost off campus. But right now, one of the things that I've been tasked with some of the colleagues is exactly how to build out this resiliency by partly combining on-campus solar, but also considering other technologies such as generation that can depend on hydrogen and other sources, at least for resiliency purposes, not to run day to day. Okay. Thank you.